Assalamu alaikum everyone. I hope you are doing well. And this is Shumona Khanum presenting before you. My ID is 20230000000192. Today I will represent research paper title Intrusion Detection System using optimized deep machine learning with explainable AI. The objective of this presentation is background of the study, find out research gap, problem statement, the problem, and future future research scope. My first objective is background of the study. In this paper, interaction detection system using optimized deep machine learning with explainable AI. This work focus on improving cybersecurity using machine learning and deep learning models, while also making the system explainable using XAI techniques. Cybersecurity is now more important than ever due to rapid increase in cyber attack and intelligence threat. Research gap. In today's digital world, cyber threats are increasing rapidly across network. Cyber threats are increasing rapidly across network, cloud system, and IoT environment. Traditional security Traditional security systems are no longer enough because attackers are becoming more advanced. Interaction in detection system or IDS help identify malicious activities in a network. However, most modern AI-based IDS systems have major problems. They major problem. They work like a black box, meaning we cannot understand how they make decisions. So even if they are accurate, they are not always trusted in real world applications. Our goal is to build a system that is highly accurate, efficient, and explainable. Despite the success of email and DL-based idea system, there are still several important gaps in existing research. First of all, lack of explainability. This is the black box problem. The most learning models work as black boxes. This means they give predictions but do not explain why a decision was made. In cybersecurity, this is a serious problem because security analysts need to understand the reason behind an alert before taking action. Limitation trust in real world deployment. Even if models achieve high accuracy, they are not always trusted in real applications. This is because decisions are not interpretable. System behavior is not transparent, always cannot validate predictions easily. So there is a gap between high accuracy and real world usability. For generalization across dataset. Many existing models perform well on one dataset but fail when tested on another dataset. For example, a model trained on one IDS dataset may not perform equally well on NSL, KTD, or real network studies. Lack of integrated approach. Most existing works focus only on improving accuracy, and very few studies combine high performance machine learning or deep learning models with explainable AI technique like SSAP and LIM. as transition of next problem statement. The main problem we identified are first, high false positive and false negatives of IDS system. Second, imbalance in network datasets, which make learning difficult. Third, lack of interpretability in deep learning models, and finally, difficulty in developing models in real-world system because security analysis cannot trust black box prediction. So we need a solution that improves both accuracy and transparency. Next, scope of the research. Our main objective are to develop hybrid to develop hybrid ideas to develop a hybrid ideas using ML and DL models to optimize model performance using hybrid parameter tuning to compare multiple algorithms like RF, XGBoost, KNN, DT, and LSTM, and to integrate explainable AI technique like SA, shape, and line. This ensures both high performance and interpretability. Interpretability. Summarize the literature review. Key contributions. CNN-based ideas for wireless network achieving 97% accuracy, and the Particular SVM hybrid model for network traffic data. Fully interconnected neural network for KDD CUP methodological trends. Transition from basic classifier to deep hierarchical pattern. The focus is shifting from pure accuracy in including XI framework like NIV and for the instructions. CNN. However, most existing work is still lack of explainability and generalization across datasets. That is where our work improves the system. Next, methodology overview. Our proposed system include several stages. Data collect from IDS and initial KDD dataset, data pre-processing and encoding, feature engineering and analysis, model training using ML, machine learning and deep learning algorithms, hyper, hyperparameter hyperparameter tuning using the grid search and random search, cross validation for performance evaluation, enable AI using shape and line. This pipeline ensures strong performance and reliability. Overview the dataset lifestyle generation, collection, processing, storage, management, analysis, visualization, and interpretation. The data reprocessing and encoding. We used two datasets. First, a cobble network interaction detection dataset. Second, NSL-KD dataset, which is widely used in cybersecurity research. The dataset 42 features. The level encoding. Normal and attack classes, attack type, DDoS, DOS attack, probe, R2L, and U2R. We encoded categorical data into numerical format for model 10. For model training, level encoding, data cleaning, and scaling and script, converting the categorical object type column into the numerical value using the level encoded for algorithm comparability, removing duplicate record and handling missing values to prevent bias in the training of the connects. Scaling and skip features scaled and divided into 17 or 15-15 ratio for training, validation, and testing phases. We train multiple models, random forest, X, random forest. Then the long-term memory, LSTM institution hierarchical temporal pattern within the parameter and values. The LSTM unit 80, gains units 32, and dropout rate 0.1, learning rate 0.01. Model training, the XG boost gain in decision tree and LST deep learning. This model was trained using part of training, validation, and testing. We also applied hyperparameter tuning and optimized performance. Cross validation strategy. We used a stratified k-fold cross validation and with k tuple equal to 5, k equal to 5. This ensures balanced distribution of classes in each fold, more reliable evaluation, reduce bias in result. The final score is calculated as the average across all four. It proves an unbiased performance average across the key equal to 5 folds. Result and conclusion. We used grid search CV and random search CV for performance matters IDS dataset XG, Boost, Random Forest, DT, and LSTM. Result indicate outstanding accuracy across all models, with XG Boost showing perfect precision recall balance. Here, XG Boost in 99.52%, Random Forest 99.52%, and highest LSTM 98.89%. This tuning improved model stability and reduced overfitting. XAI implementation, one of the key distribution, and we used Shapley additive explanations like local interpretable model, agnostic explanation. And shape helps us understand feature importance globally. For example, high source byte and destination byte strongly indicate attack. Line helps explain individual predictions, showing why a sample was classified as an attack or normal. This makes the model toward to trustworthy. IDS dataset. Cross Cross dataset validation. Test on NSL KDD dataset to verify the generalizability. Our results show very high performance. XG boast 99.5% accuracy. Random forest 99.5 accuracy. KNN 99.3 accuracy. And decision tree 99.3 and LSTM 98.89%. Overall, machine learning models slightly outperform LSTM in the dataset. Shape and line integrity shape quantifies feature contribution high and DST byte are primarily predict for anomaly class. Line explains individual local predictions, foresting trust in a specific automated decisions. In the summary, result NSL and KDD dataset. NSL and KDD dataset XG post achieved 98.62 accuracy best. This is the best. KNN and DT also performed above 98%. LSTM achieved around 97.78%. This shows good generalization across dataset. When compared with previous research, CNN 97%, LSTM RNN 97.1%, and DNN plus RF 98.5%, SVM 98.08%. Our XGBoost model achieved 98.62%, which is higher or comparable to existing methods. This proves the effectiveness of our approach. Next slide, conclusions of the summary. In conclusion, we successfully developed an IDS system using machine learning and deep learning techniques with explainability. Key achievements: high detection accuracy, strong generalization across dataset, interpretability using SISAP and LIMA, balanced performance and transparency. This makes the system suitable for real-world cybersecurity applications. And number 8 objective in future work. In future work, we aim to trust on real-time network traffic, use longer and more diverse dataset, improve zero-day attack detection, attack detection, deploy system in cloud-based IDS platform, enhance explainability feature with advanced XAI techniques. Real-time integration, deploying the framework into active networks in live thread interpretation, advanced serial ML, IoT, and Edge. References. Overview: the intrusion detection system for computers network security, computers 2025. Deep learning assignment anomaly detection, and ML and deep learning approach NIDS ECCE 2025. Ideas for wireless sensor network IEEE Access 2024, and enhancing cybersecurity and NIDS using ML RAAICON 2024. Network Instruction Detection Dataset Kaggle 2025. Thank you. Thank you for your attention. I am happy to answer any question. Thank you.